Hi guys, today I'm going to introduce the concept of buoyancy and some of its applications. Let's look at two examples. In the first example, Joey has a wooden block. He picks it up and puts it in water. Part of the wooden block immerses in water and the wooden block floats. In another example, Kelly has a weight. She puts it in water. Although the weight is fully immersed in water, the weight still sinks. So why does this happen? Well, you might say this is easy, because the weight is much heavier than the wooden block, so the weight sinks in water and the wooden block floats. But that is not the case, because if the wooden block is big enough, it will be more heavier than the weight, but the wooden block will still float in water, while the weight will still sink in water. A more realistic, however extreme example is if you consider a rock and a cargo ship on sea. The cargo ship weighs thousands of tons, but it still floats, while a rock, although weighs only maybe 1 gram, it still sinks under the sea. So weight is not the case. So then, what determines if an object will float or sink? The key to buoyancy lies in density of an object, which is mass divided by its volume. Turning this into a formula, we have density equals m over v, where m is the mass and v is the volume. Okay, now let's hear an interesting story.
The story of Archimedes and the golden crown is told because one of the kings found a golden crown that was sacred to the gods, and he was unsure whether or not it was completely gold, or if one of the smiths had put some silver into it. Thinking how to solve this problem, he asked Archimedes, who was a well-known scientist in his era. Archimedes was pondering this problem one night while he was in the bathtub, and when he got in the bathtub, he realized that the water overflowed out of the bathtub because it was already completely filled when he got in. And he realized water's displacement occurred. And he realized that that was how he could solve his problems. So he leapt out of the bathtub and shouted, "Eureka, Eureka," running throughout all of Greece. Archimedes then made two masses equal to the weight of the crown, one in silver and one completely gold. Then he filled a large vessel completely with water to the very, very brim and put the silver in it first. The amount of water that overflowed was equal in volume to the amount of silver mass that sunk into the vessel. He then refilled the vessel and placed the mass of gold into the full vessel. Not as much water overflowed because gold is more dense than silver, so the same weight takes up less volume. Archimedes filled the vessel one more time and placed in the crown that the king had given him. More water was displaced than the actual gold that he had just massed. Therefore, he realized that some of the crown must be silver, and that is how he solved the problem. This is how Archimedes' principle came about.
As Archimedes studied more on what he observed, he finally came to the conclusion of the Archimedes principle, which stated that the upward buoyancy force exerted on a body immersed in a fluid is equal to the weight of the fluid the body displaces. So what does this mean? Let's look at a diagram. In this diagram, a ball floats on water. The ball has a gravity force acting on it pointing down and a buoyancy force acting on it pointing up. The gravity force equals the mass times g, which is the density of the ball times the volume of the ball times g, while the buoyancy force equals the weight of the water it displaces, which is around half the volume of the ball times the density of water times g. So now, the gravity force is in a relationship with the density of the ball, while the buoyancy force is in a relationship with the density of the fluid, and we can use these relations to solve a lot of problems. Here are some applications. The first one is using apparent weight to determine the density of an object. As you can see in the diagram, an object weighs 7 pounds before putting into water. After putting into water, it weighs 4 pounds and displaces 3 pounds of water. So the weight of the object is 7 pounds and the buoyancy force is 3 pounds. How can we use these numbers to solve the density of the object? Well, gravity equals mass times g equals density of the object times volume of the object times g, while buoyancy equals density of water times volume it displaces, which is also the volume of the object, times g. When doing the ratio of the two equations, we get density of the object over density of water equals gravitational force over buoyancy force. Then we can plug in the numbers. Density of the object equals density of water times 7 over 3, while the density of the water is 1.0 times 10 to the third kilograms per cubic meter. Now let's look at Kelly's demonstration and do an example. She hooks up a block and weighs it. It says 18 newtons, and then she puts it in water. As the reading gradually goes down, it ends up in 10 newtons. So what is the density of the block? You probably have figured this out already. The density of the object equals to the density of water times gravitational force over buoyancy force. In this case, the density of water is still 1.0 times 10 to the third kilograms per cubic meter, while the gravitational force is 18 newtons, and the buoyancy force equals 18 minus the apparent weight 10 newtons, which is now 8 newtons. So we can calculate the density of the block. Another good application of buoyancy force is the construction of cargo ships. As we all know, a cargo ship is made of steel and all kinds of metal, which is more denser than water. So how can it float? Well, a cargo ship occupies a large amount of volume, which makes its density actually lesser than the density of water. Therefore, when a cargo ship is in sea, it displaces a large amount of volume, which produces a buoyancy force that is equal to its gravitational force. So this leads us to another question. Since a cargo ship floats on sea, how much more cargo can it actually hold in order for it not to sink? To analyze this situation, we can set up a simple model. Here we have a wooden block and we put it in water. Part of the wooden block is underwater because it needs to produce a buoyancy force that is equal to its gravitational force. While there are some spare volume above the water level, which can be pressed underwater to produce extra buoyancy force that can carry the weight. As you can see, as we gradually add in weight, the wooden block sinks with more volume in water, producing more buoyancy force, which equals to the gravitational force of the wooden block plus the increasing weight that is added to the block. Finally, when it reaches to a point that the weight is so much and unbalanced on the block that the block flips and all the cargoes are dumped into the sea. In this case, we use the wooden block to represent the ship and the weight to represent the cargo. But in real life, ships are designed in such shape that it is more easy to balance the cargo on the ship. Also, the ship will never carry that much cargo, so that the whole ship have to be immersed underwater to produce a buoyancy force that could support the weight of the cargo. Usually, a ship has a mark on the side of its body. When the water level reaches the mark, workers stop loading cargoes on the ship and the ship have to sail. Back to the model. If you want to calculate how much cargo a ship can hold, then you have to first calculate the maximum buoyancy force, which is the density of water times the volume of the ship underwater times g. And then you use the maximum buoyancy force minus the gravitational force of the ship itself, and the difference will be the weight, which is the density of the water minus the density of the object, and the whole difference times the value times g. Now let's review. The first thing you have to remember is the relationship of the density of the object and the density of water determines how an object will act in water. For example, if the density is larger than the density of water, the object will sink. If the density equals to the density of water, the object will suspend. And if the density is less than the density of water, the object will float. You can apply the similar principle to other kinds of fluids. For example, an hydrogen gas balloon will float in air because hydrogen gas is less dense than the atmosphere air, while a nitrogen gas balloon almost suspends in air because the nitrogen gas almost has the same density as the atmosphere air. And if for some reason, if you put chlorine gas in a balloon, the balloon will sink because the chlorine gas has a larger density than air. Also, it is useful to remember the apparent weight formula. The density of the object divided by the density of water equals to the gravitational force of the object divided by the buoyancy force, given that the density of the object is larger than the density of water and the object is fully immersed in water. And finally, to calculate how much weight a cargo ship or any object can carry in water, you use the maximum buoyancy force minus the weight of the object. Last but not least, I have a 10-problem quiz for you guys to practice. The teacher will give out the quiz and hopefully you guys don't flip the table like me when I'm making this video.